What a pleasure. So nice to meet you.
Yes, nice to meet you as well.
Introduce yourself.
My name is Jeff Beck. I have been a computational neuroscientist for the last 15 years or so. We study, we do a lot of things. We're interested in the Bayesian brain hypothesis. We study how humans and animal behaviors can be modeled as Bayesian inference. So there's a lot of like animal and human behavioral modeling involved, but we're also critically interested in how the brain can actually implement the operations of probabilistic reasoning, how the brain encodes information as information quite literally, but in particular how it encodes probability distributions and how neural circuits can perform the operations of probabilistic inference.
Fascinating. Maybe we should touch on the brain first. Do you think the brain acts as if it's performing Bayesian inference, or it actually does?
Yes. No, so I'm refusing to answer your question, right? Because what's the difference between as if and actually does, right? So from my perspective, does it matter, right? Whether the brain, so I'm going to model you right now, okay? And I could model you either 100% accurately, whatever that means, or I could model you as if you were performing Bayesian inference. So which is preferred?
Well, I guess if you said what's the difference, could you argue that this Bayesian modeling is sufficiently fundamental to explain everything we need it to do?
So I think that it's fundamental to empirical inquiry, period, right? At the end of the day, the best thing you can do is a Bayesian model. And I think you can make a variety of arguments as to why it's a normative take on empirical inquiry, period.
I completely agree with that. So Bayesian analysis is beautiful. It's one of the most principled things which exists. So I think of it actually as a continuation of logical reasoning, but in the domain of uncertainty.
Yeah, well, in any empirical domain where you are relying on uncertain information, relying on sense information, where you are trying to make statements about something that you do not directly observe, right?
Yes, yeah. Yes. So reasoning about uncertainty and what is unobserved. Okay, this is really interesting. I mean, maybe this is an aside, but the only potential issue I see with Bayesian analysis is the dependence on some kind of structure which represents your domain. And it feels to me like there are an infinite number of possible structures that could have predictive power. So there seems to be a kind of chicken and egg situation of how do we know we've got the right structure? And what valence does the structure have? For me, the structure has to be intelligible by other humans. So there are presumably some structures that would work really well that wouldn't make any sense to us.
Mm-hmm.
So how do we find the right structure?
Right. So what would be ideal, right? So the ideal situation, okay, so all knowledge is conditional, right? I think we can sort of say that, right? And it's conditioned on two things, right? It's conditioned on the data that you have acquired, what you call your list of facts, right? And the models that you have considered. So I'm going to replace your use of the word structure with model, right? So I have a bunch of different models for how the world can work, and I represent them probabilistic, so it's a generative model, right? And then I want to choose the best model that I've got, right, based on the data that I've observed. So my conclusions are based on those two things, right? The data and the set of models that I have considered, right? And so ideally, what you would consider all possible models, all possible structures, rely on the automatic Occam's razor effect of Bayesian inference to tell you which model is like the most likely model in a given domain, or maybe just in general. We of course do not do that because it requires some sort of insane exhaustive search. We cannot possibly check the set of all possible models, but that's what we would like to do. Yeah. But we can't. But it sort of doesn't matter, right? From a practical perspective, we could sort of I'll only consider the models to which I have like computational access, like I can actually like evaluate in some way. But we can always rely on this sort of automatic Occam's razor effect to tell us which is the best in a fairly normative way. Does that make sense?
Yeah, it does, absolutely. So, as you say, there are many appeals to infinity when we talk about machine learning and Bayesian analysis. There's like, universal function approximators, and you can talk about this infinite selection of models and so on. But we live in the real world. We have practical computational...
Right, and so we only ever consider a finite number of models, and that's fine. There's nothing wrong with that. And you could even describe science as being composed of fundamentally two steps, right? Data acquisition and then exploring the space of models. All models are, of course, wrong, and I like to paraphrase Einstein just a little. Instead of saying, but some are useful, I like to say some are simply more wrong than others.
Yes.
Right. But it's still just a model. I mean, when I occasionally pretend to be a philosopher, I tend to say things like, a proper Bayesian places no metaphysical significance on the parameters and latent variables of their models. It's just a model.
Yes.
Right.
Yes.
I don't. An electron is a label for an equation, not something that it's controversial, I guess, but not something that exists. It's a label for an equation. That would be a sort of a very extreme, borderline Kraysian take on Bayesian reasoning.
Yes, indeed. Okay, well, let's talk about where we're at with active inference then. So we already, we've been doing machine learning for many years, and that seems quite sclerotic and rigid because we train a model, we do it offline, and it gives us something which is akin to if we did maximum likelihood estimation in the Bayesian regime, and then we just go and run it. Usually we run it on stationary data. We don't run it in an agent framework. Usually there's only one of them. And what we're talking about now is with this active inference is we have an agent framework. Every single agent has a model, and we're actually acting in our environment. We're seeking information, we're getting information back, and we're dynamically building our model. And that, in some sense, is akin to this model search process that you're talking about, but it's very efficient. It's got some interesting properties.
Right. It has sort of optimal experimental design built in. It allows the agent to sort of run around and say, hey, look, what's the data that would actually be the most informative data? I should go get that, right? And that's to some extent what we do in the lab, right? What we don't just sort of run around taking pictures of things and say what the hell is going on, right? We design an experiment to help us separate different hypotheses we have about how the world works, right? Let's build that into behavior. It's been remarkably effective in the lab. Let's build it into behavior. And I think that's one way of summarizing what active inference is.
Interesting. Okay. Empiricism is quite an interesting thing because it kind of implies that you can follow the data. And there are some folks who think that it's not possible to do that, and you need to have a priors that tell you something about the world in order to do that. But I guess maybe we should start with that. So if you're just empirically searching through the data, because we humans have this magical ability to perform abduction, right? Because you're talking about these hypotheses. We seemingly just grab them out of thin air, and we're searching this exponentially large space. And if I said to you, well, cynically, if I followed the data empirically, maybe I wouldn't be able to find those hypotheses. What would you say to that?
I would say it's a good thing that we've been born with a rather elaborate set of models, right? That have been refined by evolution and discovered to be useful over time, right? We're not doing so unlike like a machine learning algorithm, right? It's not doing we don't do de novo inference. Yeah, we do inference based on a great deal, millions and millions of years of information that we've incorporated to inform our priors and to give us a good starting point to allow us to do inference quickly and efficiently.
I'm so on board with that. Yeah, so I'm a huge fan. There's no predictions without assumptions. Our priors, through some process of magical resonance, we've been endowed through the laws of nature with these cognitive priors, these primitive priors. And to what extent do you think they're universal? I mean, because I'm a big believer that in some sense there's no magical pure intelligence, right? These priors tell us something about the environment that we're in. All intelligence is situated, specialized. I mean, would you agree with that?
Yeah, absolutely. I'm not sure what you mean by universal, though, in this context.
Well, so GoFi people, I've got many friends, GoFi friends, and they believe in they've got a kind of computer science approach to intelligence, and they say the located in prior is universal. It would exist even if the universe didn't exist, or contains in. I put something in a container, I put the container in the other room, the thing is now in the other room because it's in the container. Or the semantics of events, for example.
Gotcha. Okay.
They argue that, and I can get on board with there being, let's say, natural priors and social cultural situated priors. don't necessarily have to exclude one to have the other.
Right. Okay. So universal is sort of things that necessarily follow, which is, it's sort of like saying like, well, if I were to sort of think about all of the models that I could build, right, all of them there are certain kinds of relationships that necessarily must exist. Right?
Yes.
That's the idea.
Yes.
I mean, I think that's true. I'm not sure how I would formalize that or necessarily make use of that, but it certainly is the case that like some models you certainly want to avoid models that contain inherent contradictions or make inference really hard. And so that sort of like gives you some constraints on the set of models that you'd like to consider. I don't know about like when I build a model, what do? I start drawing circles and I say this latent variable talks to this one in some way and it talks to this one in some way, and that imposes my structures. Like the graph is the structure. Yeah. And I can sort of put them together completely arbitrarily. And so I don't see how there's like, like fast and strict rules other than like there are, all the relationships are probabilistic. And so you're talking about some sort of high level semantic logical operations that are necessarily true. Yeah. And that makes a lot of sense to me, but that's not actually how I at least tend to do things when I construct a model, right? These loose probabilistic relationships that have some kind of structure, like a tree structure or a line structure or a circle structure. And but they don't often map they map neatly onto causal thinking, but not necessarily neatly onto logical thinking, right?
Yeah, well, I mean, there's an interesting interplay between the two ideas. I mean, Go-Fi folks and rationalists, they're I think quite similar, but they think that knowledge is a binary. So they only exist in the domain of certainty, and we're much more flexible than that. We can think about
that probably explains why I glitched out for a second there, because I can't think in a binary way, right? You have probability distributions over absolutely everything. There is very little outside of mathematical knowledge that you have any certain like Laplace said it quite nicely, and I'm going to butcher the quote, of course, but all knowledge is probabilistic, right? And he meant all knowledge about the empirical world, right? About the universe in which we live. All conclusions are conditional. They are conditioned as I said before, they're conditioned on two things, and they are probabilistic, right? They're conditioned on your models, they're conditioned on your data, and all conclusions come with error bars.
So what you're saying makes sense to me, and I agree that in the domain of limited information and uncertainty, then absolutely. But would you concede that there are any situations where you do have complete knowledge about something, so it's a binary?
I mean, well, okay, so what's a fact? Right. This is one that I like to poke my students with. Like, what's the defining characteristic of a fact, or if you're like probability theorist, an event, right? Those are the things that you can say occurred with probability one. Yeah. Right. And if you're a Bayesian, it's the stuff you put on the left side of like P of data given model, right? Yeah. I can see somebody sort of saying, oh, well, there are certain things that are facts, right? Like, but I have very difficulty seeing which things are facts. Like, you can tell me this happened, but I still have to I still have to solve a probabilistic reasoning problem. Like, are you honest? Yeah. Did it actually happen? Are you delusional? I can, sort of like come up with all sorts of other explanations as to why you might assert something to be true, which which don't necessarily involve it actually being true. Yeah. Right? Okay. So maybe my model has a binary variable in it, which is it's true or false, right? Yeah. But my conclusions never do.
Yeah, that's interesting. I mean, we don't need to talk about Go-Fi people for too much longer, but I think in the 70s they were trying to solve a simpler version of the problem, and a lot of this comes from reasoning. I mean, they say language models don't reason, and by reason they mean kind of like filling in the semantics. So there might be missing data, and with these cognitive priors, I can kind of like fill in the missing data by doing some reasoning over the top. Now, it's not to say you can't do that with a probabilistic model, but now you're kind of sampling, and I guess the complexity comes in when there are many possible models, right? And there are many possible ways of filling in these semantics and doing this reasoning, and that's where, in my mind, I'm not saying it's a problem, but that's where like it gets a little bit blurry for me.
So it is blurry. It's blurry by design, because blurry is best, is how I would respond to that. And it's sort of like, I understand that. I certainly, it would be very nice, and it would be very sort of psychologically compelling and pleasant if we could say this is the model, right? And this is how the world works. But that's not. But I would say that that's not an empirically accessible conclusion, right? It's always there will always be uncertainty, and we should just be okay with that, right? We should just be like, well, and at the end of the day, what's science really about? Is it about discovering truth? No, science is about prediction and data compression and nothing else.
Yeah.
Right. We don't evaluate the quality of our model based on how true it is, because we can't. We can only evaluate the quality based on its ability to predict out of sample data.
Okay. I mean, I'm fascinated by this idea of, well, Maxwell spoke about an integrated approach of internalist and externalist cognition. So you have agents that model themselves, that model other agents, and also you can kind of think of abstract boundaries that incorporate many agents, and agents will have different behavioral complexities. Some will mimic each other. So, you've got this whole ecosystem of agents, and they are modeling something which may or may not. I mean, I think it probably does bear some resemblance to ontological reality, because there's some kind of consensus mechanism between them, but it doesn't have to be. It can be almost an entire hallucination. But it's a really interesting way to think about building a model by kind of distributing it into an ecosystem of agents that sense make with each other. I mean, like, how do you think about all of that?
So one of the things that I find very appealing about like the free energy principle and the Markov blanket story is that it's sort of it's very much fundamental to how it is that systems work, right? So something that hasn't been, I think, emphasized enough in the literature is the relationship between like systems identification theory and like Markov blanket studies. So how do you make a nice, like, compelling, like, relatively simple model of like the universe? Well, you start drawing circles around things and you give them labels, right? And you sort of say, oh, no, this is a subsystem. This subsystem behaves in this certain way. And this is great because now I can summarize all these complex interactions with some relatively simple set of equations, right? And then I can just do that over and over again and have like rules, right? It's taking this complicated set, this massively high dimensional set of observations, and reducing it down to a few simple this is like statistical physics, right? We're going to reduce it down to a few simple macroscopic variables. The Markov blanket story is saying, well, actually, we really want to reduce it down not to a few simple macroscopic variables like temperature and all that stuff. We want to describe subsystems. We want to segregate our environment into entities, objects, right? Subsystems that then we can describe. And that's exactly what it's for, right? It's for taking this very, very complicated system and dividing it into something that is simpler. We can call those things agents. We can call them objects. The beauty of the Markov blanket thing is that it gives us a definition of an object type based on the statistics of its boundary, which is the probabilistic equivalent of systems identification theory. You don't care what's going on inside. Two objects that have the same boundary interact with the universe their environment rather in the same way, and are therefore same object type, right? So this is it really is sort of, it's just a very useful way to solve a dimensionality reduction problem that's really, really, really complicated.
Yeah.
Right.
Okay. So active inference is the process of, creating such a model or allowing a model to emerge.
Well, I would separate. So active inference is sort of how we, if one way to think about active inference is that it's if you'd start dividing the world into these subsystems, and subsystems that exist for any amount of time must have achieved some sort of homeostatic equilibrium with their environment, right? And then you could sort of say, well, okay, how did they do that? Like, what's up? And it's sort of active inference sort of necessarily follows from that. If you have achieved a homeostatic relationship, right, you are doing some kind of you are doing some sort of prediction about your environment and reacting to it in a way that allows you to maintain your identity.
Okay.
Right. And here your identity is the statistics of your boundary. The statistics of your Markov blanket is what determines your identity.
Yeah.
Right.
Yeah.
And everything, any object can be characterized this way. Even stupid objects, right? Rocks are doing terrible inference about their environment, but you can still model them using the exact same set of equations because as an object, it has a blanket.
Okay,
right.
okay. A couple of thoughts on that. So I'm trying to link it to just cognitive science in general. So we have these abstract categories and we have, words and semantics. They point to those categories. We communicate in words. And you could argue whether language is a system of thought or communication, but it doesn't matter. We've come up with this representational system to communicate with each other. And in a sense, I guess what I'm getting at here is we're implementing a kind of mediation pattern. Right, so the categories, the words, the things that we use to communicate with each other, they mean something to us. There's an intelligibility component to it. Because, yeah, we both agree that we need to have a map to represent the territory. We need to simplify the map, not only for our own existence and planning, but also like communication and social complexification. So it feels like there are some guardrails on the type of models we build, not necessarily about representational ability, but about social complexification.
So what do you mean by guardrails, right?
Well, I guess like in order for me to mediate with you, so for you to understand my model and what I'm talking about, it feels like there's a trade-off between representational fidelity and communication ability.
Okay, so what I'm going to do is I'm going to answer the question I think you're asking and hope it's the question that you are asking. So communication, so I would like to communicate, maybe say my model to you. So I have this model in my head for how the world works, and I'd like to communicate it to you. This is actually a really difficult problem just in general. Like, and we use language to do this. That's what language is ostensibly for, right? But how do we do that, right? Because the model that I have is internal to me. I have some abstract state space, and there's absolutely no way you could know what my abstract state space is because it's in my head, right? Yes. It is not in yours. And I'm trying to communicate something like that, that it contains a representation to which you have no access. Okay, so what do I do? Well, what I do is I try to communicate it to you in a way that makes my model grounded, right? Mm-hmm. And so one way to do that is consistent with this sort of prediction and data compression view of science is to make sure that I don't communicate to you, hey, like right now we're in state number 7. And then you go, oh, well, I think we're in state number 9, so 7 and 9 must be. Okay, we could do it that way. But another way to do it is all I ever communicate to you is effectively predictions.
Yeah.
Predictions live in the domain of observation space, right? Mm-hmm. They're the grounded form. That's the grounded thing that comes out of your models. I can tell, well, the cat's about to walk into the room and things like that. Mm-hmm. And then, if I communicate to you solely in terms of predictions, right, then I don't need to know what your internal model is. I don't need to understand the structure of your internal model. I am now speaking in the language that you necessarily understand. Now, this is the caveat that I should have started with. I am by no means an expert in like language and linguistics and how they speak. This is just me randomly now thinking about like, well, how would you make communication work between two agents that have like two complete, that almost surely have two completely different models for how the world works.
Oh, undoubtedly.
And the only thing that I can think is to make it grounded is for them to speak in the language of prediction, right? I think you are going to do X, and I think this is about to happen to you.
But on that though, yes, I completely agree. So it reminds me of sort of Jeff Hawkins' view of we've got the matrix in our head, we condition each other and so on. But our phenomenology could be very, very divergent. We're just mediating through prediction. But the thing is, I think it's a bit almost magical to say, we're mediating through prediction. What is a prediction? The domain of that prediction is the environment that we're in, right? So
that's right.
Yeah, and so in a sense, there is an environmental dependency on that mediation process.
Right.
Yeah.
Because I mean, if you think about this in terms of like agents and blankets, right? One of the, when we model things in that framework, it's always the case that a blanket or an agent is embedded in an environment, and two agents cannot share by definition of what a blanket is. Like two blankets cannot be shared, right? If blankets start to overlap, what do they become? They become one thing, not two things, right? Yeah. And so all interactions are mediated by the environment within this sort of modeling framework, right? Mm-hmm. And so communications are mediated. I communicate to you. It's like my voice goes out, but it actually goes through the environment and makes it to your ears, right? And it's the same way, right? Is that so our communications are mediated by the environment. So odds are we are in some sense speaking in the language of the environment.
Yes. Yes. Exactly. Okay.
Again, but not an expert here. Just
no.
Some of this is like random speculation. Yeah,
we're all speculating when it comes to semantics and meaning. And by the way, what you said really resonated with me. And I'm fascinated with the emergence of meaning. I spoke with Daniel Dennett recently all about this, and he's got some very interesting ideas about the intentional stance and stuff like that. But it's really weird when you talk about phenomenology and meaning and the hard problem and the intentional stance. So many people just think, it's intellectual masturbation. You're kind of talking about this philosophy of mind, this weird way of thinking about things. And I'm always left with the question of, what is the cash value? Like I think it's a really good reference frame for us to understand and communicate these ideas. But as Carl said yesterday, well, there's no real phenomenology. It's just their world model. It's their
it's just a world. It's just a world model that includes other things that are probably somewhat like me. Like, you know, one way to think about philosophy of mind, right, that sort of abstracts away the whole philosophy part is, I need a philosophy of mind because I need to be able to predict your behavior.
Yes.
You know, it's that simple. It's that pragmatic.
Yes.
You know, it might be nice to have a coherent philosophy of mind that told us something like really profound. But if you're a harsh instrumentalist, and I tend to sort of go in that direction when behaving as a scientist, you don't.
Yes.
All you need is the ability to predict someone else's behavior. Having a theory of mind is really helpful to that end. So a theory of mind is also about prediction and data compression and nothing else.
And just before we leave theory of mind, are you a materialist? Are you, you know, do you believe that certain? I mean, we're talking about certain organizations of material here in a certain pattern, which potentially gives rise to, let's not call it, you know, conscious self-awareness, but something which is as if it is a mental state. So you're kind of no nonsense in that respect, are you?
Well, it depends on like the day of the week and what pair of pants I'm currently wearing, right?
Yes.
It's sort of like, you know, when functioning as a scientist, that's sort of foundational. I think that's implicit in the entire approach, right? Is that there is this, you know, but when I'm wearing my like Buddhist Quaker pants, right, it's like, you know, I obviously have a very different view. and I don't, you know, it's, you know, so I often don't know how to answer that question, like, I don't know, completely, because on the one hand, you know, when I'm functioning as a scientist, right, you know, harsh instrumentalist, that's, you know, that is the approach I have committed to taking.
Yeah.
Right. But when I'm sitting around, like, thinking about how, you know, how things really work and, like, you know, what I care about and things like this, I do believe, like, crazy things like, oh, there is a moral center to the universe, right? You know, there are, like, non-arbitrary notions of right and wrong, right? And so, but, you know, I don't bring those to work. Right.
Yeah. Well,
you know, you know, and I do have a lot of, like, sympathy for Schrodinger's view, right? It's all mind.
Yeah, yeah.
You know,
and
you know, you could talk to, like, I don't know, I came across the term neo-materialism the other day, and my first thought was, well, what's the difference between neo-materialism and neo-idealism? Because if I were to put neo in front of either of those words, it would end up meaning the same thing.
Yes.
Right. And so is it all mind? Does mind arise from matter? I think those are both real possibilities.
Yeah, interesting.
But I'm more inclined, like my intuition is more on the sort of idealist view, like it's all mind.
Oh, interesting.
And
objective idealism. Yeah. So you still think there's some kind of
that's where I lean, but that's not where I work.
Yeah. And I mean, but speaking for myself as well, I mean, I guess I compartmentalize. I mean, we're a science podcast, and in the science, I mean, there was that letter recently about IIT and panpsychism, and many philosophers talk about philosophy of mind. They say it's a reductio ad absurdum, which implies panpsychism. Therefore, we must throw it out. And I'm thinking, I don't have a huge problem with panpsychism. It's not massively dissimilar to people who think that, you know, certain configurations of material give rise to mental states. Like that's just as spooky as saying all material has mental states because it's a property of the universe. Does it, you know, for people just to say, no, there's a bright line and that's pseudoscience and that's not pseudoscience, that seems a bit ridiculous to me.
Well, I mean, I have some sympathy because you use the word science, right?
Yeah.
To say that, you know, this is why, like when I come to work and function as a scientist, I put on my materialist pants, right? And
well, but could I touch on that? Because I think that there might be a little bit of empiricism bias that I'm hearing. The only reason I say that is because you said it's all about, you know, compressing, representing the data. But I mean, Chomsky would say language models, the reason they're not a theory of linguistics is, like, you know, a scientific theory should say, why are things this way? Why are things not this way? And I get, even like you were saying with morality, you know, it's not, Hume said you can't get an ought from an is, you know, so he's saying empiricism doesn't work for some things. There are some things where, you know, we've got this magical process and we say, no, things are this way, and the data, I've got that from the data.
Yes, I like to say that the rookie error of moral philosophy is confusing is and ought. And so when I'm at work, it's I'm living in the is world. Like, what is, like, how do things work? You know, how do I make good predictions about the future and things like that.
Yes. Yeah.
And it's like orthogonal to how the world should be, right?
Absolutely. But yeah, that's fascinating. Well, we should talk about, you know, you're doing some really interesting work with optimization. Now, the biggest problem, I would say, not problem, but challenge with this Bayesian approach to building multi-agent systems is that we have a kind of computational complexity that grows exponentially with the cardinality of the representation. The representation is a discrete representation, which is really cool. Oh no, it's not. It's not.
No.
I was going to like contrast it to Jeff Hawkins' HTM, because he was an example of a guy doing very exciting stuff many years ago, which wasn't neural networks. Now they've gone back to neural networks. But tell me, what are you working on?
Okay, so there. My belief is that the project of most interest is tractable Bayesian inference.
Yes.
For large models, scaling things up, and one of the tricks that we're doing is we want to do like gradient free learning, and so it's sort of very different than how your large language models are fit, right? You calculate your gradient, you take a little step. Yeah. One of the nice things about being Bayesian or Bayesian reasoning is that it enables you to construct certain classes of somewhat limited models, right, for which you can do inference and learning in very big steps in parameter space. And so you're not, being a little loose with language here, but you're not like computing gradients and taking little steps and following to their optimum. Instead what you're doing is you're looking in a particular direction in parameter space, and because you've constructed your model in a certain way, you can just sort of say, oh, if I look to the north or the south, I can see that, the actual minimum of my objective function along that line is right there, and I just teleport to it. And then I look east and west and do the same thing over and over again. That's what I mean by like gradient-free learning. We're not just following a path to a minimum. We're taking these massive steps in parameter space. Now, this has been known for a very long time, but this approach was kind of abandoned because the belief was, right, that you could really only do this for a very limited set of generative models. And it's true. Right. As soon as you say, I would like to do this sort of like coordinate descent learning, or however you want to put it, and take these massive steps, you're basically constraining yourself. Right. You're saying that the allowable set of models is really limited. And so it's kind of like abandoned. It's sort of like pushed to the side. Because what we really want is we want like a probabilistic programming language like Pyro, which I do love, by the way. I think Pyro is great, right? Because you can specify any generative model, right? And your approximate, and then like make some statements about your guide or your approximate inference algorithm. Just press go, and it does gradient descent, and it finds the solution. It's incredibly powerful. It's not super fast, but it's incredibly powerful. But you can get a great speed up and improvement if you don't make something so general. And so that's the approach that we've been taking. It was, as I said, it was abandoned because it is a limiting approach. You cannot just specify any old generative model. An arbitrary generative model cannot be specified in this framework in such a way that it allows you to do this sort of fast, big step gradient-free learning. Yes. But it turns out, and this is the reason why I got really excited, recently is that they're actually the class of models that you can use are actually pretty darn powerful. In fact, the attention module that makes that you could argue really made large language work, the transformer. Yeah, information retrieval. It turns out the transformer is in this class of models.
And what class is that?
The best way to put it would be, what's a transformer? A transformer is ultimately a mixture of experts model.
Oh, it's so interesting because there are 20 different descriptions, and that's one of them.
That's my favorite one, and the reason it's my favorite, and if you just if you write down a mixture of experts model, a certain kind of mixture of experts model, and then say, okay, well, what's the inference algorithm, right? So it's a generative model, so there's like some latents that you'd like to infer. And you say, well, what's the inference algorithm for it? Yeah. And then you can say, oh, look, well, first I have to do this calculation, and then I have to do this calculation, and then I have to do this. You can map those exactly onto literally exactly. The structure of the equations is identical to what a transformer does. There's a few exceptions, like, there's no like added norm step, right? But it's just a normalization. It's not really doing it. This is how I rationalize these things. Yeah. So if that's the case, right? If what is currently believed to be the most powerful component, right, of large language models, the thing that really made it work, right? So this is the self-attentional transformer, is implementable. If you can learn the parameters of that, in a gradient-free way, in this perfectly in a Bayesian way with gradient-free learning, then at least in principle, right, you should be able to do anything that like a large language model could do. And you might even be able to learn it faster. Like if you look at learning rates on your gradient descent, right? How does it start out? So here's my loss function, right? So this is bad loss. This would be good. And eventually you're going to get over here. And you start learning, you're doing gradient descent, and your loss function is like not doing squat, right? It's not changing, not changing, not changing, not changing. And at some point, the algorithm starts to learn something, right? And your loss goes down and down and down and down. And then there's this, in fact, there's often a very rapid decrease and then a long period of refinement. Right. The beauty of doing gradient free learning is you get to skip that initial phase where the model is doing terribly. You can get rid of all of that in just a few iterations of these sort of coordinate descent steps. Right. You can get to a pretty not awesome, not like perfect, but you can get really good, really fast learning out of it. When you take this approach.
So there's quite a few things I want to pick up on there. And first of all, so one of the, maybe we should just talk about some of the assumptions. So there's you have to make assumptions all over the place. And the reason why gradient descent is so ubiquitous is because it makes certain
always works.
Well, it always works, and weirdly, because we always had the curse of dimensionality, but weirdly in stochastic gradient descent, more dimensions are better. There are more paths to a basin. We find the basin very quickly. If anything, my experience doesn't completely jive with yours. When I look at training runs, you always get this characteristic exponential, kind of decline on the loss function, and then this.
But you don't see two phases, or you don't see a struggle phase followed by a rapid learning phase followed by a struggle phase followed by another learning phase, right?
Well,
we tend to see that because you get because you do have these sort of saddle nodes in your loss function, right, where you can sort of you get to something, it's not actually a minimum, but the gradients slow down and they speed up.
I guess I have seen it, but I guess the weird thing is when I've looked at training runs, especially the larger the model, it's almost like there's a law of averages thing going on where it just converges on this kind of power law distribution, and it always looks the same. But that's the thing. So it's about how we encode representations in a vector space. So we make this, essentially they're all curves. There's a surface to it, and we're traversing this surface. And now we're saying, okay, well, we want to work in a domain which is potentially discrete, so we have discontinuities, and it's a completely different representation of the target problem. We want to do gradient-free optimization. And I guess you're kind of saying the trade-off is that we're making certain assumptions now in this domain that
we're using a limited set of models, and that's the ultimate trade-off. The ultimate trade-off is that you can do gradient descent with any loss function, right? And autograd is, you can blame autograd for everything. Autograd is why we do it. It works so well, right? I when I was a kid, back in my day, we had to compute those gradients ourselves. And so now, of course, we have this amazing tool that does it for us. And that's one of the reasons why it's become so popular. The coding has become so easy. And it really is truly amazing, right? That's the beauty of that approach. The beauty of that approach is that gradient descent learning is accessible for any loss function. Whereas this kind of learning is not accessible for any loss function, right? You have to, it's really only accessible for a certain class. And that, again, was why, I suspect this is why it was dropped, right? Because you're placing limitations on the class of models that you can consider. But if that class is powerful enough, right? If it includes transformers, right? If it works not just in discrete domains, but with continuous variables, and does and makes it easy to mix the two, which is actually what really makes it work, is the mixing of discrete and continuous. Then maybe this isn't that big of a deal. Maybe we should be doing this instead, right? Maybe this is a route forward for fast learning, for fast online learning, for something that really resembles one-shot learning, not where you've actually snuck the task in the back end in the data that you trained on, but you're able to sort of say, no, I have this brand new data, and it just takes a couple iterations of my algorithm to get me to a not the best solution, but to a reasonably good idea of how I should proceed.
Okay. So with this gradient-free optimization approach that you're working on, I understand it might be domain-specific. There might be different flavors depending on the approach. But if we just take a representative example, what's the time complexity? How does it relate to the cardinality of the data, the way that the data domain is represented, etc.?
That question is very model-specific. So I guess I could answer it by giving an example. Is that all right?
Yeah.
Okay. So. in a dynamic setting, it's no more laborious than running like a simple forward-backward algorithm over time, right? It's no more laborious than like a Kalman filter, right? It's on par with that, right? I mean, you know, there's a few extra calculations that go in there, but the complexity is on, you know, if you're just, it's not more sophisticated than that.
Yeah.
Right? I think that's probably the shortest answer that I can give without like feeling I need to dive for a pen and paper.
Yeah, interesting. And we are in a kind of continual learning setting now as well. I mean, because I think just from a mindset point of view, a lot of folks are still in this mindset of, you know, offline batch training, no agents, and this is a completely different setup. But if you're observing this, like the dynamics of this over time, how are you measuring it? What does good look like?
What does good look like?
Yeah, so let's say you've got a multi-agent system, and you're I mean, presumably you would even represent the data generation process as an agent in the system. I don't know.
Which we do. Yeah. So I can tell you about like the Markov blanket detection algorithm that we have, if you like, which is sort of like it's not designed for necessarily predicting what an agent will do. It's designed for sort of, you know, identifying what an agent is and typing it, right? So the output of the algorithm is something like, you know, there's in like the fun version of it, like, you know, there's a cell, and the cell is like going through, you know, it starts out as a blob of dots, and it evolves, and initially it evolves like something that looks like a cell membrane. This is in particle linear, if you're familiar with particle linear, which is a really cool simulation.
It's cellular automata. Yeah.
If you haven't played with it, if anyone's listening who hasn't played with it, particle linear is a blast, right? It's actually, it's a great toy.
Yeah.
And so what happens, right? You start out with a blob of particles, and then they kind of form into a cell membrane, and then there's some stuff in the middle, and it's just sort of like oozing around, and then the cell membrane develops these like flagella, I guess you could call them, right? Yeah. And then meanwhile, as the flagella are evolving, to use the term loosely, right? A cell nucleus is evolving too. Like the stuff in the middle goes from being like blobby to being compact, you know, to being like, you know, a compact thing, a compact little circle with like little organelles that are sort of like, you know, zooming around it in some way. And so what would you like? What would you like to be able to do with like a simulation like that? Well, what you'd like is you'd like an algorithm that sort of says, that's the cell membrane, right? That's the nucleus. And you'd like it to be based solely on dynamics. And so that's what we did, is we sort of said, okay, any given scene, right, is composed of a bunch of elements that are all moving around and they're interacting in some way. And we're going to model that as a bunch of objects, which again in this lexicon is like the same as agent, right? Because they have, you know, each object has an internal dynamic, right? It has a boundary that it interacts with the environment with, and then there are lots of these things, right? And so we specify that structure, and our macroscopic model of the whole system, right, is going to consist of a bunch of these guys, right? And then we just fit it. Right, so we sort of say it's like, you know, we're going to find like n objects, and the way that we're going to fit is by looking at the dynamics, right? Who's interacting with who? So the way I like to think about this is that you can think about this in terms of like dimensionality reduction, right? I have all these particles in my system, and I would like to cluster them in a way, right, that sort of says, oh, these guys go together. They're all interacting strongly, and there's a simple set of macroscopic variables, which all have their own dynamics, that determine how they interact with their environment and each other to some extent, though interactions between the objects is always mediated by the environments. So...
Well, I mean, a few thoughts on that. I mean, first of all, linear is absolutely amazing. We did a show on Emergence, and we were talking all about Conway's Game of Life, and linear is basically the continuous version of that. Yeah. And I think there's a couple of other tweaks as well. So most of the time in cellular automata, you do synchronous updates, but I think this has like a stochastic update.
It's also just beautiful, right?
It's absolutely, it's amazing.
It's gorgeous to watch, right?
It's amazing. I think there's a channel called Bert Chan where he's got loads and loads of visualizations of linear. But yeah, I'm glad that you gave that answer though, because that was kind of the direction I wanted to go in. So in the artificial life community, they build lots of like emergentist systems like you're describing. And I always have the question that, okay, so I've now essentially grown this system. So this system has taken on very complex functional dynamics, and you know, like we can categorize some of these phenomena, like macroscopic phenomena, like gliders. Yeah. And we can build recognition algorithms, and we can like look at, as you say, objects that interact with each other and so on. But it kind of feels like now we're in this space where, you know, we were talking about mediation and intelligibility earlier. Like, you know, we've got no way really of describing, other than like in very simple terms, what's going on in this system.
Right. So well, I'm going to parse that out as saying, like, a lot of times when we do that kind of categorization, there's a lot of like post hoc analysis and rationalization is why we would call this a thing and that a thing, and it's sort of like, yeah, that's the beauty of the approach that we're taking is that it's completely agnostic as to what a thing is. It just says that whatever a thing is, its dynamics can be summarized as having a Markov blanket. Right, and that's it. That's all we assume. And the beauty of the approach that we're taking is that you can have different kinds of objects. So what does the algorithm discover when we apply it to this like particle linear thing? Well, what it discovers is that the cell membrane is a kind of object. That's like object 1. I'm just making up numbers, right? And then the initial blob that's kind of nucleus-like in the middle is like object 2. And it discovers that. And why does it discover that? It discovers that because the particles that make up those things are strongly interacting with one another in a way. And, you know, and so we can treat them as having some low-dimensional dynamical systems representation. And then there's a blanket, and they're sort of weakly interacting with everything else. And that's all just sort of discovered, you know, by the algorithm. But then the cool thing is that as the cell membrane develops flagella, right, what ends up happening is that the algorithm says, oh, that's not a cell membrane of type 1 anymore. That's a new thing because it has a new kind of dynamics, right? So the dynamics tell us like what kind of thing we've got, right? And you get all this for free. Right. Now, some caveats. Does it work perfectly? No, nothing works perfectly, but it works well enough that we get sort of reliable results. And my suspicion is the version 2 of this algorithm, which will have access to more sophisticated dynamical systems modeling under the hood, right, will be a lot better, and will start to be, you know, like truly an amazing thing.
So this is fascinating because I've always believed that for an approach like this to work well, you know, we're dealing with essentially complexity, and I think that the way that systems like, you know, like artificial life type systems overcome overcome brittleness is by using this kind of self-organization and emergence. So you have to start from the bottom and let it emerge. And I can really see something like that working, obviously with the caveats that we just spoke about. But I think like some of the other implementations of active inference are bootstrapping halfway up. So they're kind of saying, okay, well, rather than like emerging from the primordial level, I'm going to like take high-level abstract agents, and you know, I'm going to start with this kind of like factor graph cognitive model, and I'm going to like, you know, have some bootstrapped representations from some neural network encoders or something, and I'm just going to like start the thing now and let's see what happens. And it kind of feels like starting halfway up the stack can introduce brittleness.
I'm going to have to think about that. I mean, I think one of the reasons that people do start halfway up the stack is because they're trying to solve the same problem. You know, active inference is solving the same problem that like reinforcement learning is solving. And so we sort of, you know, a lot of cues are taken from that community as to like what the right level of modeling is, you know, what kind of pre-processing of my images should I do, and sort of things like that. It's just sort of the common approach. And I think that's why it's, now could you know, does that institute brittleness? I don't have a good answer to that question. I don't really know. But I you know, what I like about active inference in this setting is, you know, the way in which it defines or motivates an agent, right? The fundamental difference between active inference and Bayesian reinforcement learning, as far as I can tell, is the definition of an agent. Right. So how does reinforcement learning define it? An agent consists of 3 things, right? It consists of an inference engine, a prediction model, right, and a reward function to motivate behavior, right? So the prediction model is, given the data that I've already seen, what's my prediction for how the world is going to work? The inference engine is how it learns that, right? How it learns what that model is. Right, and then the reward function is what motivates behavior. Reinforcement learning. So one of the fundamental questions that I think like Carl has done a really good job of sort of dealing with, or pointing out that like this is a real issue that we need to really deeply think about, is where does the reward function come from? So this is, by the way, the caveat here is this is my take on active inference. This is not the uniform take on active inference. But so where does the reward function come from?
Per agent.
Yeah, for any given agent, where does it come from?
Yeah,
like you know, and you know, to wax philosophical or pretend to, because I don't really know how to do it for a second. It's like there is no normative solution to the problem of value function selection, right? Like how do you decide like that's the right reward function or that's the right reward function, right? And so the answer that active inference gives, I think, is very sensible. The reward function is not the way you want to motivate behavior. The way you want to motivate behavior is by saying that an object has to, is sort of this link back to systems identification theory, right? An object has to be what it is, right? And what it is defined by its input out, its relationship to the environment. Yeah. So reward functions in active inference are replaced by an expression of homeostatic equilibrium via the statistics of the blanket. Right, and so this is a robust. Actually, I am getting back to your question. I swear to God. So this avoids brittleness, but probably not the kind of brittleness that you were asking about, right? By saying that the goal of the organism is to achieve homeostatic equilibrium, as opposed to optimize some monolithic reward function, right? You create a more stable system. In my view, right? I mean, and let's face it, reward function specification is dangerous, right? The last thing you want to do is tell Skynet to end world hunger and have it decide that the appropriate solution is kill all humans, right? Yep. Whereas if you told it, no, here's how the environment currently is, right? We just want to achieve some kind of equilibrium that looks like this, but is a little different.
You are preaching to the choir.
Oh,
yeah, I know Rich Sutton had this paper out called "Reward is Enough," and I completely and utterly disagree.
No, reward is a dangerous. It's playing with a loaded gun.
100%, and not only that. I mean, it's not too dissimilar to, like a lot of utilitarians have similar problems thinking about that reification of reward. But anyway, no, this is really interesting. So I guess what I was getting at though is with linear, the agents are actually emergent, and when you see the agents crash into each other in linear, they repair themselves, they heal themselves, they kind of like they develop this global coherence from some underlying primitives. And then when we go one step up, we now explicitly model the agents, and that's okay because we've just had a conversation about this, and we think there's something universal about the concept of an agent, right? So now we explicitly model them, and then we're talking all about, okay, well, there's this teleology question with rewards. And then we're kind of thinking, well, actually, a lot of people say there's something universal about the concept of a goal as well. But the individual agents don't have goals. Goals are emergent properties of the system. So, like traditional GoFi people would actually model one level of abstraction higher with explicit goals. But we kind of think, okay, well, there's also something universal about this concept of survival. So all they need to do is focus on resisting those entropic forces. They survive. And then the system as a whole will goals will emerge. But I guess it's just interesting how you can model at all of these different levels of abstraction. And I'm not saying that it would overcome a lot of brittleness. Like you could use active inference, you could build an agent framework to represent, let's say, a city or like a supermarket or something like that. And you can swap in the agents because they have clear interfaces. You can have some agents that specialize in different things. And I can understand how this could overcome a lot of brittleness, but it's all about making that kind of trade-off on that ladder.
Yes.
Yeah.
I certainly agree. So so one of the I always my mind always starts to wander when I hear the word emergence because I've never quite figured out what it means exactly. And
love to talk about that.
So perhaps I should ask a question, but I think what the other option here is that like so one of the things about so in Linea, right? So they specify this sort of, so it's learned by gradient descent. They specify an objective function, and the objective function is find something that persists, and it must persist and have a certain set of properties. So, for example, there must be like a local motion filter must generally go in like a particular direction. That's one way you can build a Linea agent, right?
I think there are many ways. So I think the linear that I'm thinking of is just a cellular automaton. So it's basically Conway's game of life. It's just very, very simple. You're just sliding a filter over, so it's overlapping and you're just performing a fixed set of rules. But the reason
well,
why
no, but the thing is, when they get those really ripping cool gliders, like, and not in Conway's scale, I mean in sort of the continuous version of Linea or in particle Linea, the way that they get to those is they say, well, look, I don't know what kind of particles should make up my, like, I would like to have an object that has this macroscopic behavior.
Yeah.
Right. And I don't know how to build such an object. So what I'm going to say is that, well, the object is made up of a bunch, this is in particle Linea, the object is made up of a bunch of particles, and those particles have rules for how they interact. And I'm just going to do gradient descent on the rules for the interactions of these different types of particles, right? So that I achieve what? I achieve a macroscopic, a target macroscopic behavior.
I understand what you mean.
And and this is why I like Linea. So what is it doing? It's saying, no. The definition of an object is that it has a target macroscopic behavior, which you could parse out. It's not exactly right, but it's pretty easy to see how one might map that notion of what a thing is and how they get to a thing onto, what's a target macroscopic behavior or target, set of macroscopic states? Oh, that's like that's a representation of a homeostatic equilibrium.
Yeah, no, that makes sense.
And so it's all kind of one framework, I guess, is the direction I was trying to go with this. Is that the beauty of active inference? A lot of the utility of active inference, is this link to like homeostatic groups. That's how you get cool things. It's one way to get like agents to form de novo. Is you sort of say, well, no, I have my goal state is that something has a certain degree of complexity and some class of interactions with its environment, and those persist over time. That is exactly how, not exactly, it is coarsely how they specified their objective function for learning in particle Linea.
Well, yeah, so let's talk about that. So some fascinating things there. So first of all, just to clarify that, and I love this concept of steering an emergent system. So it's like macroscopic optimization. So you have
this target macroscopic behavior, and then we're just going to like make, and then we'll say, well, what parts and pieces do I have to put together to get there? Yeah,
I know. And the reason I don't know whether you saw this example from Alex Maud-Vincef, but he created a CNN. So basically, a CNN is just a filter very similar to Linea, but he did gradient descent on the weights of the CNN, so that when you ran this thing in a generative setting, it would produce an entire lizard or something like that. So you're training the network at the microscopic level, and then when you generate with it, it produces this global coherence of a picture of a lizard, and then you can delete parts of the lizard and it will just grow again, right? Yeah. Because it's like self-repairing. But I think that the key thing is that the filter is fixed after you've trained it. But anyway, the reason why I think this is interesting though is when you start steering. So we want to build a distributed multi-agent system, and we want the agents to be as autonomous as possible. And when you start having this outer loop, which is kind of steering them with some fixed objective, how is that so dissimilar to the reward problem that we had before?
So yeah, that's so a really good question is so it so okay, I'll tell a story. Okay, so here's my story. So I've got some environment, and I'm going to put a bunch of agents in it, and I want it to be stable. So I imbue each agent with a definition of what it means for it to be in homeostatic equilibrium with environment, and I put all these little suckers in there, and then they just go about doing their thing, and because they have this homeostatic goal, right, that's what they achieve, right? They achieve some sort of balance, and everyone's getting along, and maybe they're like isolating. Some guys are like, oh no, I'm over here, and I don't want to deal with you guys or whatever. But basically, the system is stable, and there are all these like agents, and they do interact a little, right? But maybe only weekly or however. But now what we want to, and we can build that. We can build that in like an active inference setting, right? Because we just established this homeostatic goal, the agents achieve homeostasis with, in this sort of global, right? And there's lots of them. Okay. Now we have a problem, right? We've achieved homeostasis, but we haven't done anything, right? Now what I want to do is I want to tell my agents, hey guys, like, can you go get me a coffee? Or, I don't know what to make up, like some stupid task, right? Yeah. So that's new, right? That wasn't like built into their like, definition of self. That wasn't built into their like, that's not part of their equilibrium. Now I want to guide their behavior to get them to do something. It is a very interesting question to how to get these in, because remember, these are independent agents, right? They've learned to maybe, in order to achieve homeostatic equilibrium, they maybe have learned to like coarsely communicate with one another in some way that we could like tease out if we want to do a hell of a lot of data analysis or something like that. Yeah. But that's all that they can do. But that's not what we want, right? And so it becomes a very interesting question is how to get them to temporarily break from their homeostatic state to do what you want, right? And I can see two approaches to this, but this so we are now back into speculation phase. I feel it's important to say, right? So and we'd like to do it without suddenly giving them a reward function, right? Or giving them a goal. Okay, so option one is that we just included the set of all things we'd ever like them to do, right, as part of their like definition of self, right, their homeostatic. So for example, like you have an agent that its belief is that 3 times a day, or maybe 6 depending on who I'm working for. So it's my agent. It's like 6 times a day I know I have to go get Jeff a cup of coffee. Right. And it's built into his equilibrium, and he just sort of does it. But of course, I'd like to like bias him towards doing it when I want him to do it. And so we can just include, so one way to get that to happen would give us the ability to like perturb his internal state or poke his boundary, right, in a way that causes the right reaction to go get coffee, right? So I can go in and I can figure out, well, what's the right way to poke him, to disturb his equilibrium, to push him into a state. Now, how you would do this, that would require, I don't know, right? That's going to require like some amount of work, but it should be possible, right? He knows to achieve homeostatic equilibrium, so there should be some way for me to poke him to get him to engage in one of the behaviors I have told him is part of his homeostatic. It's like I want the ball to roll downhill. How do I make that happen? I put it on the hill. Right. And so there's got to be a way for us to like manipulate the agents directly or poke their boundaries to get them to engage in a particular task that they already know to behave it, that they've already learned is one of their tasks because it was part of their definition, right? I get Jeff coffee 6 times a day, right? And it's just a question of how to poke them to get them to like respond with that particular behavior when we want it.
Yeah.
Option one.
But just on that, because I think we agree that we want to do it in a way which doesn't introduce brittleness or change the machinations.
Right. So that's why we include it in their definition of self. That's how you avoid brittleness, right? I tell this agent that part of your definition of self is you bring me coffee 6 times a day.
But that's the thing. So it's the same thing. So it's the same existential imperative. All of the actions that the agent does, it's using this kind of balance of energy and entropy. All of that stuff stays the same. But I guess like the worry is that by creating something which might look like a fixed behavioral profile could introduce brittleness. But that's not how we would do it, is it? We would actually model it more abstractly in terms of a kind of behavioral complexity that needs to be maintained, because the behavior might change over time, right? We need to maintain that flexibility.
Right. Yeah. So I mean that's the hardest part. The hardest part is when you've taken an agent and you've told it that this is its job, and that doing this job every day is how it achieves like homeostatic equilibrium, like it gets me coffee 6 times a day. And then I'd like to change the job. Right now I want to use this agent to do something that it's never done before. That's the harder problem. Right. Yeah. And that's the problem where, well, what are your options? Well, I could just go in and change its definition of self. I could just sort of say, oh, well, instead of like 6 times a day, maybe the doctor has been had a serious conversation with me. And it's like, now I only want coffee 3 times a day. We could insert that sort of thing into its definition as well, right? We just change its definition of self. We change the kind of homeostasis that it tries to achieve with its environment, right? To get it to do something on average that we want it to do.
Wouldn't an alternative be to make the agent die and have a specialized agent with adapted behavior rather than have like, complexification in a single agent?
Yeah, so I had a rather fun conversation with one of my colleagues a couple nights ago at dinner, where the conversation of what do you think the AI apocalypse is going to look like, right? And my response was, well, actually, it's not going to look like anyone suspects, because what's going to happen is the AI agents are just going to start killing each other in an attempt to protect us from each other. Like they're going to like divide into 2 camps, and like half the AI agents are going to like obliterate the other half because they're trying to protect us from them. It's going to be a terrible, terrible apocalypse, but the only thing that's going to die are the artificial agents. that was that'll be the first one. Now, that's just one kind of it. This, of course, was a half serious conversation.
Yeah, well, no, that's what Schmidhuber said that to us.
Yeah.
No, I don't have a lot of patience.
Right, and
for
so
those.
that's another way to do it, right?
Yeah.
Is that the agents, you want a new agent that does something a little different, right?
Yeah.
But still achieves this nice homeostatic equilibrium with the environment, so the system is not brittle. You just like kill off the old one.
Well, yeah, and the reason I
Replace
say that is because you guys call this approach natural intelligence, as I understand, because it's based on...
Yeah. Now it's based on natural selection.
It is, and I guess this is a great example of if we were trying to, bootstrap this halfway up and have agents that do multiple things. I mean, that wouldn't happen in nature. In nature, they would just die, and a new specialized agent would take its place because you have this kind of niche selection. So that sounds good to me. This has been amazing. Thank you so much. I really appreciate your time.
Awesome. No, it's been a pleasure. I always enjoy these sorts of conversations.
Fantastic.
Do you have any terminal questions for me, or anything that?
Well, I mean, what are you working on? What's happening over the next year or so?
Well, let's see. I mean, many things. So, we're at on the theory side, we're working on really formalizing this link between systems identification theory and Markov blanket detection. On the pragmatic side, the multi-agent Markov blanket detection algorithm, that could do everything from like scene segmentation, object tracking, the whole 9 yards. Building, deep transformer-based neural networks that do gradient-free learning. I'm very excited about that. We have like the components are built. We just got to like start stringing them together. And then of course there's all the robotics and the AI projects. So we're going to use the same model that does the Markov blanket detection. Is effectively saying that like objects are agents, right? Everything that has a blanket can be considered an agent. And so there's absolutely no reason why we can't use this and turn this model around. And instead of using it to say what is an object, what is an agent, to sort of say, oh, well, now I'm just going to say these are agents and they do certain things.
Yes.
The mathematics is identical. The model is the same. It's just a question of, are you doing inference on observed data, or are you achieving a specified homeostatic equilibrium with all of these objects? Yes. And so I'm really excited about seeing how well that works. And we'll see.
And one final question. I did mean to ask you this earlier, and I got waylaid, but because it's quite similar. When I was playing with Jeff Hawkins' HTM algorithm, it was beautiful, but it was actually lacking one thing that neural networks did very well, which was representation learning. And transformers, for example, and as we were saying, many different ways of interpreting what they do. I mean, I like the idea that they're basically they act as a continuous database where the key is the prompt. But anyway, like a lot of folks that look into equivariance in neural networks, they think of them as quite plainly a way of introducing permutation equivariance in respect of sets. So they're a model for dealing with sets, and there's something very universal about that, because when we build these predictive architectures, I guess where I'm going to with this is on top of doing all this Bayesian update and like agent framework stuff, we actually need to build priors in for doing representation encoding. And I guess that's not really something we've spoken about.
We have built, and I really should publish this. It's like killing me that I haven't. We've built 4 different kinds of transformers, right? That are fully Bayesian. They're fully generative, right? And they do exactly that. Like they do different kinds of. You could think of it as like permutation learning, right? Because it's basically like the starting point for that analysis was kind of fun. It's like, well, suppose that you had like you had data generated from like some sort of like hidden Markov model, right? So it's like first time point 1, then time point 2, and sort of goes along like that. And then some bastard came along and like shuffled the time indices and didn't tell you what it. Okay, you could think of that. That's what that is the looking for. So you're basically asking the question like, how do I unshuffle? Yeah. Like the time points, and you can think of that as like that's the fundamental operation that a transformer is for. But there are many ways to have. There are many generative models that have like those different powers that do that sort of thing in various different ways. And so we've built like 4 of them, and that's another area of interest. Is we really want to see like what are these really good for? Like, do these solve the same problem? They are subtly different. They have slightly different properties. The manner in which they look like a transformer is that the mathematics of the inference is very, very, very similar, but they have different structures. So yeah, that's another it's a really interesting question. Is do these generative models for transformers have the same performance and properties as the standard gradient descent-based learning models of these transformers? And we don't know.
But not only that, I would go one step further. So I think the agent framework allows us here to do something that the neural network folks could never do. And what I mean by that is, have you noticed all of these models in your predictive architecture? You can actually have a kind of heterogeneous architecture. You can have multiple inputs with multiple encoders, and you can bring them in and have MLPs and so on. But it's very monolithic. It's all left to right. And now, in principle, you could have multiple agents in a multi-agent system, and they all have basically different encoders. And you and I can agree that there's probably we need to have some kind of a library of priors. And there are a library of primitive encoders that do primitive things like, things like permutation equivariance and like spatial reasoning and stuff like that. Have a bunch of agents to do all of these things. And all of that complexification and like information sharing, that will emerge, right? So we don't need to explicitly code that like we do with neural networks.
Yeah, you don't need some overlord or god like watching everyone and telling who to talk to. Yeah.
And I don't think that's been done yet. So that would be very interesting.
Yeah, no, it absolutely will be. And I'm very excited to see how that turns out, to see what sort of communication you do get between objects, right? How sophisticated does your model of the environment in which they are embedded have to be in order to get them to communicate well? And these are all like incredibly interesting questions, and I'm super excited to see how it all turns out.
100%, because they say neural networks are biologically inspired, but I mean this I think is far more biologically inclined, so we need to do that. Anyway, absolute pleasure. Thank you so much for joining us today. It's been amazing.